Good evening, everyone. It gives me immense pleasure to present this guest lecture on simulation of thermal systems, a comprehensive research case study. Thermal system simulation has become an essential tool in modern engineering, enabling engineers and researchers to predict heat transfer behavior, optimize designs, reduce developmental costs, and improve the product performance before physical prototypes are built. Today, we will explore the fundamentals, numerical methods, practical applications, research methodologies, and the future trends shaping this exciting field. Now, we will discuss the today's lecture roadmap. In today's session, we will explore following 8 different modules. First, we begin with an introduction to thermal system simulation and its significance. Next, we discuss the mathematical foundation and governing equation behind thermal analysis. We then examine major numerical techniques, including finite difference method, finite element method, and finite volume method. After that, we review real-world heat transfer case studies and CFD applications. We will also explore research methodology, modern model validation techniques, industrial application, and emerging technologies such as artificial intelligence and digital twins. By the end of this lecture, we will gain a comprehensive understanding of thermal simulation and its research potential. Now we will move on to the basic introduction to thermal system simulation. What does exactly thermal system simulation refers to? It refers to the use of fundamental mathematical models and computational techniques to predict the temperature distributions, heat flow patterns, and thermodynamic behavior within the engineering systems. Simulation allows engineers to perform virtual experiments without constructing expensive prototypes. Its importance lies in reducing development costs, shortening design cycles, and improving the system reliability. Thermal simulation integrates multiple engineering disciplines, including heat transfer, fluid dynamics, thermodynamics, and mass transfer. So, simulation began in the year 1960 that has been considered as a major tool for nuclear engineering has evolved into sophisticated computational models capable of handling millions of mesh elements and highly complex physical phenomena. Now, with this introduction, we will move on to the classical mathematical foundations and governing equations. Every thermal simulation is based on fundamental physical laws. Fourier law describes heat conduction and relates heat flux to temperature gradients. Energy conservation equation, often called the heat equation, governs the transient heat transfer within the materials. Newton's law of cooling models convective heat transfer between the surfaces and the fluids. The Stephen Boltzmann law explains thermal radiation exchange between bodies. For systems involving fluid flow, the Navier-Stokes equation governs the momentum, transport, and fluid motion. Finally, thermodynamic closure is achieved through equations of state such as the ideal gas law. Together, these equations form the basic mathematical backbone of thermal simulations. Now, let us understand the basic difference between finite difference method, finite element method, and finite volume method. Since The analytical solutions are rarely possible for practical engineering problems. Numerical methods were employed for this purpose. Under the numerical methods, now we are going to discriminate the three following key terms. First one is the finite difference method or FDM. So this is very simple and computationally efficient, making it suitable for regular geometries and basic heat conduction problems. The finite element method excels in handling complex geometries and provide high accuracy in solid thermal analysis. The finite volume method is widely used in computational fluid dynamics because it naturally conserves mass, momentum, and energy. Each method has unique advantages and limitations, and selecting the appropriate technique depends on the problem being studied. So, heat transfer simulation case studies. Let us now examine some practical case studies. The first example involves fin analysis, where simulation was used to optimize the fin geometry and improve heat dissipation efficiency by 17%. Second case study focuses on the shell and tube heat exchanger analyzed using three-dimensional computational fluid dynamics techniques to maximize the thermal effectiveness. The third example addresses electronics cooling where thermal simulation reduced hotspot temperature significantly in a CPU heatsink design. The final case study investigates solar flat plate collector where transient simulations improved collector efficiency and thermal performance. These examples demonstrate how simulation drives innovation and optimization across various engineering domains. So we now discuss about computational fluid dynamics application in thermal engineering. Computational fluid dynamics, or simply say CFD, has become one of the most powerful tools in thermal engineering. The CFD workflow typically involves problem definition, geometry creation, mesh generation, boundary condition specification, solver configuration, post-processing, and validation. In gas turbine blade cooling, CFD predicts the metal temperature and cooling effectiveness, whereas in HVAC application, CFD helps to optimize the thermal comfort and airflow distribution. In automotive, engineers use CFD to improve radiator performance and engine cooling. Similarly, data center operators rely on airflow simulations to reduce energy consumption and enhance the cooling efficiency. So thereby, CFD enables engineers to visualize the phenomena that are most difficult or impossible to observe experimentally. Let us discuss few research methodology and model validation. A successful thermal simulation study follows a structured research methodology. The process begins with a thorough literature review to identify the research gaps. Next, a physical model is developed based on the governing equations and the empirical assumptions. The model is discretized using an appropriate numerical technique. After solver implementation, results must be validated through experiments or benchmark data. The validation metrics such as root mean square error, mean absolute error, R squared values, and grid convergence index are commonly used to evaluate the model accuracy in terms of solution difference. It is important to remember that the simulation results are only as reliable as their validation process. Let us see some of the industry application and software ecosystem. Thermal simulation has transformed multiple industries. Say in power generation, it supports boiler, turbine, and condenser optimization. In aerospace and defense, it assists with thermal protection systems and engine cooling. Automotive applications include battery thermal management and engine cooling design. HVAC systems utilize simulation for energy efficient building design. Electronic industries depend on thermal analysis for cooling high performance devices. Several software platforms dominate this field, including ANSYS Fluent, ANSYS Mechanical, OpenFOAM, MATLAB, Console Multiphysics, and Star CCM Plus. Each tool offers specialized capabilities for different thermal engineering challenges. So, the future trends and research opportunities. The future of thermal simulation is closely linked with emerging technologies. Say, artificial intelligence and machine learning are accelerating simulation speed through surrogate models and physics-informed neural network. High-performance computing enables large-scale simulation using graphical processing unit and cloud-based resources. Digital twin technology combines real-time sensor data with simulation models for predictive maintenance and operational optimization. Quantum computing, though still in its early stages, holds promise for solving complex CFD problems at greater speeds. Additive manufacturing and multi-scale modeling are opening new avenues for advanced thermal management solutions. These technologies represent exciting research opportunities for future engineers and scientists. What are the following key takeaways from today's guest lecture? As we conclude, let us summarize the following key messages from today's lecture. Simulation has become more inevitable in modern thermal engineering. Selecting the right numerical method is critical for obtaining accurate and efficient solutions. Validation remains an essential component before simulation results can be trusted upon. Future engineering challenges increasingly involve multi-physics interactions that require integrated simulation approaches. Artificial intelligence is rapidly transforming the field and creating new possibilities for faster and smarter thermal analysis. Most important thing, numerous research opportunities remain available for innovative and motivated engineers. So finally, I thank you all for your kind attention and participation. I hope this lecture has provided valuable insights into the world of thermal system simulation and its role in engineering research and industry. Thank you once again.